Hi, I'm Dr. Hansen, the biochemist at A.T. Still University. I look forward to meeting all of you when you arrive this fall. In the meantime, I'm hoping you will work through these preview videos in biochemistry. In particular, I hope you do not just listen to them, but rather slow down. There are some very simple principles that if you slow down and focus and make sure you clearly understand them, it will make your learning about human disease and human health much more efficient. Certainly, it will be easier to understand biochemistry if you initially learn to understand the underlying language. As you work through these videos, I'm hoping that you will not hesitate to email me or phone me in my office with any questions. Having quick, expert answers to questions which you develop as you work through these videos will enable you to learn at a much faster rate. And of course, in medical school, you have to learn at a pretty fast rate. Anyways, work through the videos. If you have questions, call me. And when you get to A.T. Still University, stop and say hi. Let me know what you thought of them. Look forward to seeing you.
There's a precise order in which you should work through these pre-matriculation videos. First, there's a single pre-quiz for biochemical nomenclature, and you want to take that before you go through the video. The whole point is, what do you know about biochemistry right now? And please don't even worry if you have trouble on the pre-quiz. We expect you will. This is for you to make some assessment of your level of knowledge. After you do the pre-quiz, you should do the vodcast. I guarantee that the more slowly and deliberately you take your time and work through these videos, the faster you'll get through them, and the more they'll benefit you when you get to A.T. Still University. After the vodcast, there's a post-quiz. The learning objectives for biochemical nomenclature begin with enzyme nomenclature. I want you to be able to interpret enzyme names to understand their function. In order to interpret the names of enzymes or of any pharmaceuticals or biological reactions, you need to understand the underlying parts of these names, basic organic nomenclature, which you did learn probably in the first 2 or 3 weeks of beginning organic chemistry. So this is something you want to kind of refresh yourself on. You absolutely need to know what an acetyl group is versus an acetate or hydroxyaldehyde ketone. Also, part of organic nomenclature is knowing how to use Arabic numerals or Greek letters in naming the carbon atoms in an organic compound. And finally, I will describe in detail the most widely applicable organic mechanism used in life, really in your interest to fully understand that.
The most powerful concepts in science are also the simplest concepts in science. Unfortunately, education, starting from preschool and going all the way through college and medical school, often puts people under pressure to where they have to resort to brute force memorization of gibberish. Certainly, I know I've done that time to time. I've had to memorize these words for this test, how to fill in this blank. And really, that's mostly a waste of time. It's much more powerful to be able to interpret complicated words than it is to memorize the infinite number of possible names. To illustrate this example, let's start by looking at a small list of enzymes, most of which are very biologically and medically relevant. And in fact, this is only a partial list. I would hate to memorize alpha-ketoglutarate dehydrogenase without being able to interpret it. N-acetylglutamate synthetase, phenylalanine hydroxylase, 17-alpha hydroxylase. These are all very complicated names, yet they're built on very simple building blocks, much like life itself. I do not recommend that you memorize any one of these names, but by the end of the year, you should be able to interpret all of them. And let's begin by just thinking about the grammar of enzyme nomenclature. When you see an enzyme name, the first part is the subject, the second part is the verb. So we look at alanine transaminase. The subject, it acts upon alanine, and what does it do? It transfers an amine, and it's an enzyme. Whenever you see an enzyme name, don't just memorize syllables without understanding them. Always try to figure out linguistically how to interpret it. For example, to memorize the name of all of these kinases without recognizing that each of them catalyzes the same reaction would be a profound waste of your time. And you should absolutely know that kinase means an enzyme which adds a phosphate to something. Now, this is one of the weird names because most of the names make sense. Dehydrogenase means it takes a hydrogen away and it's an enzyme. Lactate dehydrogenase takes a hydrogen away from lactate. Why does kinase mean that it adds a phosphate? You don't need to know this part of it, but never hurts to sort of have insight into the nomenclature. So kine is from kinetic or activity, right? The first kinases discovered were enzymes that activated other enzymes. Specifically, they activated other enzymes by adding a phosphate group to them. Now, it turns out that adding a phosphate group to an enzyme induces a conformational shape which could activate it, but in other enzymes, that conformational shape inactivates it. For that matter, you can add a phosphate group to sugars or to other substrates. But at the same time, kinase, the origin of the name, has to do with the word kinetic that was involved in activating enzymes at one point. So interpreting the name kinase to simply mean an enzyme that adds a phosphate group to something, irrespective of activation or inactivation, fructokinase adds a phosphate to fructose. Phosphofructokinase 1 does not add a phosphate to fructose. Instead, it adds a phosphate to phosphofructose. Specifically, it adds a phosphate group to fructose 6-phosphate to make fructose 1,6-bisphosphate. How about phosphofructokinase 2? It specifically adds a phosphate to fructose 6-phosphate to make fructose 2,6-bisphosphate. Pyruvate kinase adds a phosphate to pyruvate. Interestingly, AMP-activated kinase does not add a phosphate to AMP-activated. This is where the subject-object can be confusing. Rather, AMP-activated kinase is a kinase, an enzyme that adds a phosphate to something, and it is activated when adenosine monophosphate is high in a cell. So high levels of AMP cause AMP to bind to this kinase and to turn it on. Likewise, mitogen-activated protein kinase is a kinase that adds phosphates to proteins, and it turns out that that kinase is activated by mitogens. Mitogen, can you interpret that? Mito for mitosis, gen for genesis or generating. So a signal, a hormone that generates mitosis, it will activate this kinase to phosphorylate proteins, probably as part of some signaling pathway. And if we look at hexokinase, an enzyme that adds a phosphate, and it adds it to a hexose, a 6-carbon sugar, ose. Hexokinase, a shortened form. It grabs ATP and glucose, adds the phosphate to the hexose. Nobody should be memorizing all of these names, but you should begin to be thinking, oh, a kinase phosphorylates something. How about a dehydrogenase? A dehydrogenase is an enzyme that takes a hydrogen off of a substrate. Whenever you read the name lactate dehydrogenase, go, oh, it takes a hydrogen from lactate. Oh, it takes a hydrogen from pyruvate. Oh, it takes a hydrogen from glucose. Oh, it takes a hydrogen from alpha-ketoglutarate. Oh, it takes a hydrogen from alcohol. These enzymes are deeply involved in a lot of diseases. For example, a deficiency of glucose 6-phosphate dehydrogenase is the most common human enzyme deficiency, and it can be quite harmful. Lactate dehydrogenase? Well, lactate dehydrogenase is part of the Cori cycle that links liver metabolism to red blood cell metabolism. Pyruvate dehydrogenase deficiency can lead to neurological disorders. Alcohol dehydrogenase involved in alcohol metabolism and therapeutics for alcoholics. Acid aldehyde dehydrogenase. This is one of the reasons that when Asians drink alcohol, they often get very red-faced. This one category of enzyme and the various substrates it acts upon are very medically relevant. Most of the enzyme names that you look at, you don't even need me to tell you what they mean. For example, can you tell me what a carboxylase will do, what a decarboxylase will do, and what a hydroxylase will do? These are very important enzymes. Please pause and answer the question. Okay, a carboxylase, ase means it's an enzyme, il means linked to, carbox is referring to a carboxylic acid. A carboxylase adds a carboxylic acid to some substrate. Okay, how about a decarboxylase? Again, these are so obvious, if you just think about them, you're going to understand enzymes. A decarboxylase removes a carboxylic acid from a substrate. For example, glutamate decarboxylase removes a carboxylic acid from glutamate. Dopa decarboxylase removes a carboxylic acid from dopa. Pyruvate carboxylase adds a carboxylic acid group to pyruvate. Acetyl coenzyme A carboxylase adds a carboxylic acid group to the acetyl group of coenzyme A. How about a hydroxylase? Hydroxylases adds a hydroxyl group to something, basically a OH group and alcohol group. This is how simple a lot of enzyme nomenclature is.
Nonetheless, I really want to emphasize carboxylases and decarboxylase enzymes. They're very medically important. I want to show visually the exact activities I described. Can you legalistically interpret pyruvate carboxylase to explain this reaction? Okay, so ase means it's an enzyme. The first word is pyruvate, so that's the substrate. Il means linked to, so pyruvate carboxylase adds a carboxylic acid group to pyruvate to make oxaloacetate. You need to understand what a generic carboxylase enzyme is. I chose pyruvate carboxylase as an example because it's so medically important. Pyruvate carboxylase is used to regenerate citric acid cycle intermediates. It's a step used in gluconeogenesis, so it is a very important enzyme. And one other point I should make is, look, we've added the carboxylic acid group, but it should be over on this side of the equation. Where did it come from? Biotin is a coenzyme made from one of the B vitamins, and it can activate our carboxylic acid group so that now it can be passed to pyruvate. As carboxybiotin becomes decarboxylated, pyruvate becomes carboxylated. And one more detail, not crucial to this talk, but it's always best to think on the most basic level about all of the nomenclature. Carboxylic acid is not something you need to memorize. It's something you need to interpret. Carb has a carbon atom. Ox has oxygen atoms. Ic acid, it's an acid, or as shown here, it's the conjugate base, carboxylate, of the acid, carboxylic acid, as we'll describe in the pH talk coming up. Now, how about a decarboxylase. Can you interpret the name to tell me what a decarboxylase will do to this compound? Please go ahead, interpret the name. Okay, the name, ase, this is an enzyme. D, it removes carboxyl, a carboxylic acid group, from the substrate glutamate. Now you look at this and say, wow, but which carboxylic acid group does it remove? And I'm going to say, you don't need to memorize that, okay? You just need to interpret the enzyme name. That's the learning objective. Now in this case, I will show you that glutamate decarboxylase actually removes the alpha carboxy group from glutamate to make a 4-carbon compound called gamma amino butyrate. And have you ever heard of GABA before? So this is really important in terms of neurotransmitters, and you're going to study that a lot. It's so easy for the electrons in a carboxylic acid to resonate down to the carbon to reform double bonds so that you have carbon dioxide coming off. The electrons that link the alpha carbon to the carbonyl carbon can resonate down onto the alpha carbon, which can grab a proton, and there you have your GABA.
Let's go for another one. How about a synthase, a synthetase, and a bisphosphatase? I'm not worried right now about distinguishing between a synthase and a synthetase. What do you think they do? Well, a synthase synthesizes something, and a synthetase also synthesizes something. A much lower priority is to distinguish between them. A synthetase is something that makes something, and it requires ATP to do it. So for example, delta aminolevulinic acid synthase is the synthase that makes delta aminolevulinic acid. Gamma glutamyl cysteine synthetase is the enzyme that makes gamma glutamyl cysteine. However, in order to do that, it must burn an ATP. Glycogen synthase is the enzyme that makes glycogen. Glutamine synthetase is the enzyme that makes glutamine, and it requires an input of ATP. It must hydrolyze ATP to make glutamine. How about a bisphosphatase? Well, a bisphosphatase is much like a phosphatase. This is not as much information, but it just gives an ase is an enzyme that does something with phosphate. And I will say that we already know that a kinase adds a phosphate to something. So what does a phosphatase do? Well, it removes a phosphate. Again, it's not as obvious as dehydrogenase, transaminase, synthase, carboxylase, decarboxylase, but a phosphatase, a little bit of memorization, but mostly understanding that it's kind of the opposite of a kinase. I'm hoping you see now that many enzyme names precisely describe exactly what the enzyme does. Other enzymes tell part of what it does, and at least they will point you in the right direction. So let's finish off now. Can you tell me what a lipase, lyase, aromatase, phosphorylase, and reductase do? Go ahead and try to interpret them, but I'm going to move on. A lipase, well, lip is short for lipid, and ase does something to it. Again, it gives you a clue, it points you in the direction. Specifically, lipases are enzymes that hydrolyze lipids. They break them apart. A lyase lyses something, so it breaks something apart too, not necessarily a lipid. How about aromatase? Well, it's an enzyme that has something to do with aromaticity. In particular, aromatase is in steroid biosynthesis, and it takes one of the 6-membered rings and makes it aromatic. These are beginning to get specialized, and we'll look at them in more detail throughout the next year. One of them that is tricky is phosphorylase. You'll notice that's different from phosphatase to break off a phosphate. We will look at phosphorylases in detail because they're very important. They do not break off a phosphate. Phosphatase does that. Phosphorylase, il means link, enzyme, phosphorylase links a phosphate to a substrate in order to break it apart. And in particular, we'll talk about the very important glycogen phosphorylase, which breaks down a polymeric form of sugar, and it breaks it off by inserting a phosphate group to make glucose 6-phosphate. A reductase, what does it do? Well, I can't give a lot of detail, but it reduces something. Instead of oxidizing a substrate, it does the opposite, it reduces it. And we're going to talk a lot about the very important distinction between an oxidation and a reduction early on this coming year. And I think that pretty much finishes this look at enzyme nomenclature, but I think you can see that there's a lot of information there if you just read the name. Part of learning these enzyme names, and part of learning various protein names which are going to be involved in various genetic diseases, and part of learning pharmaceuticals, relies upon understanding some rudimentary organic nomenclature that you may have learned in freshman chemistry, and you may have relearned in the very first month of introductory organic chemistry. Again, you were probably exposed to this in biochemistry, and so this is not something new, but you really should not even have to think when you come across these names. You should know that a hydroxyl is an oxygen linked to a hydrogen. It's on an alcohol. You should know the difference between an aldehyde and a ketone, a carboxylate versus a carboxylic acid. These various organic terms are at the very basis of knowing what organic molecules are. Apart from simple organic names of functional groups like amines and ketones and carboxylic acids, you're going to repeatedly come across enzyme names, disease names, pharmaceutical names that have a prefix such as a Greek letter or Arabic numerals or both. You can absolutely memorize 3-beta hydroxysteroid dehydrogenase deficiency, or gamma glutamyl transferase, or 5-alpha reductase inhibitors. But if you're just arbitrarily memorizing Greek and Arabic numerals without even understanding what they mean, you really are burdening your mind. If you actually understand what the symbols mean, in many cases you can then simply ignore them, or in some cases you'll go, oh, it's important to know that. So I now want to look at Greek letters and Arabic numerals. This is a very simple system. It's at about the complexity of grade school arithmetic to understand it. And let's begin by looking at fatty acid nomenclature. I'm always going to use simple representations for organic molecules where every angle, every end, every intersection is a carbon atom. If you see that a carbon atom, such as here, has only 2 bonds to it, you can assume that the remaining 2 bonds are to hydrogen atoms because all carbons actually have 4 bonds. So here's a more full representation of palmitate. Here's a simpler representation. The full representation is just too complicated to make sense of it, so I'll always be using the simplified forms. I want you to tell me how you would number every carbon atom in this compound. You need to pause the video, and I believe you would derive the exact same nomenclature that currently is used. Look at all that carbon. Now, what can I use as a landmark? What makes it different? Please continue. Yeah, well look, these 2 oxygens are very different from all the carbon and hydrogens in this molecule. They are the landmark. So if I were numbering this, I would start at the largest atom, I would start at the landmark, and then I would call the first carbon right at the landmark linked to these oxygens carbon 1. And then I would number to the end of the tail. I believe that you would have invented organic nomenclature the same way as it currently exists. So there should be no problem. And there are a lot of medically relevant enzymes that have a number in them because they relate to a position in an organic molecule. You don't have to legalistically find these positions, but boy, it sure makes it easier to think. What direction does DNA or RNA polymerization occur? From the 5' to 3' direction. Those are based on carbon numbering nomenclature. What if the landmark is not at the very end of the molecule? Now, how would you number this molecule where the landmark is somewhere in the middle of it? Would you please take a stab at numbering that? And then tell me the rule you would make up. You don't want to start at the landmark, because then you're going to have to somehow backtrack. You're going to go 1 to 12 here and 13 to 15 and who knows what direction here. How do you fix that? How would you make the rule? Please? You simply start at the end, which is closest to the landmark. So I say to someone, you see the mountain over there? There's a little hill next to it. That's where you start. So the number 1 rule, Arabic numeral nomenclature, find the largest atom as a landmark, go to the end of the carbon chain that's closest to the landmark and start numbering there. And I'm hoping you're saying, yes, Dr. Hansen, this is too simple. And I'm okay with that. I hope that every time I talk with you, you think that I'm being too simple. Not too afraid that that'll happen. How about taking another stab at this? Will you number the carbon atoms in this molecule? Where do you start? Where do you end? And you go, wait a minute, there's a problem. The largest atoms are the oxygen atoms, and they're at both ends. So which end do I start at? Please answer. Well, if you have identical ends, you have a mountain on each side, you need to find the next largest landmark, which is an amine. So which end do you start at? The end closest to the amine. So you start at the end of the molecule that's closest to most of the biggest atoms, so that you would number it 1, 2, 3, 4, 5. And by the way, I hope you know what this compound is. Please tell me. Yeah, it's glutamate. And if you learn anything from me, you're going to know what glutamate is. There's another system of numbering that's based upon Greek letters. And again, you see Greek letters in a lot of the terms I'll be using throughout the year. You don't have to legalistically know, but the rules are as simple as Arabic numerals. In Greek letter nomenclature, it's based upon the presence of a carbonyl carbon. Do you know what a carbonyl is? A carbonyl simply means you have a carbon-oxygen double bond. So here's a carbonyl. And in Greek nomenclature, the alpha carbon is a carbon that's adjacent to a carbonyl or bonded to a carbonyl. Will you go ahead and use the Greek alphabet to label this molecule? Go ahead and do that. You label the adjacent carbon alpha, beta, gamma. What do you call the carbon that's in the carbonyl bond? You don't call it alpha, you call it the carbonyl carbon. You could go ahead and label each of these. Again, just alpha, beta, gamma going away from a carbonyl carbon. Here I'm showing the Greek numbering of these different compounds. If you're going to use the Arabic numbering here, which direction do you go? Where do you start? And you say, well, let's see. There's an oxygen that's near this end and an oxygen near this end. How can you choose? Well, this largest landmark is linked twice. Therefore, this is the heavier end. It's in a double bond. So you begin 1, 2, 3, 4, 5, 6, 7. Let's do an experiment here. For the amino acid, will you label all of the carbons using Greek lettering? And for the acid, will you label just the 2 end carbons at each end using Greek letters? Please go ahead and take a stab at that. But I'm going to move on. Well, again, we do have 2 carbonyls, so I could call this an alpha carbon and I could call this an alpha carbon. But this is one continuous carbon chain. It'd be nice if I just chose one of them. How would I choose? Basically, I use the same approach I used for the Arabic numerals. I will call this a carbonyl and this a carbonyl. Adjacent to the carbonyl near more big atoms, I will call this the alpha carbon. So we have an alpha amino acid glutamate. So we have alpha, beta, gamma. And you'll notice again, alpha corresponds to carbon 2, because this would be 1, 2, 3, 4, 5. How about numbering here? Well, again, the alpha carbon is not the carbonyl carbon, it's adjacent to it. Although the carbonyl carbon will be called 1, the alpha carbon is adjacent to it, so this is the alpha carbon and the beta. What about at this end? Boy, I'm not that good at the Greek alphabet. Let's see. Alpha, beta, gamma, delta, epsilon, phi, I don't know. And since us scientists are not so good with the Greek alphabet, they don't label it all the way to the end. You know what they call the beginning and the end? The alpha and the omega. So in fact, alpha, beta, omega 1, omega 2. And in fact, this particular fatty acid would be called, let's see, omega 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be called an omega 9 fatty acid. It is desaturated starting at the 9th carbon from the omega end. It also turns out to be a very important fatty acid called oleic acid. Guess why it's called oleic? What does that sound like? The word oil comes from this because it's found in olive oil. It's the most prevalent fatty acid in olive oil. So if you now have some familiar with enzyme nomenclature, if you're able to number carbon atoms in organic molecules, and if you have some idea of the various organic functional groups, I hope you move on to part 2 of this fundamental biochemical nomenclature pre-matriculation talk. Thank you.